Thank you for joining this panel. A few months ago, an atmospheric science professor told me he wanted to move the faster growing data from a packaged software to the cloud. But his students, his graduate students, did not have the skill to do that. About the same time, a computer science professor told me he wanted to offer a big data course, but the computer science department had no big for the students to work on. So see, at one side, the big data, but no computing skill. At the other side, with lots of computing skill, but no data. And sometimes we find it difficult that they can talk to each other. So we have a dream that someday, students of all scientific disciplines may have the skills in computing as good as in mathematics or in language. That someday, the students of computer science departments may have the knowledge and easy access to the data of all disciplines in science. Computing in science is the theme of this summit. We have two panel discussions. In the morning, the topic is how to foster interdisciplinary talents. It's more on education. And in the afternoon, will be on interdisciplinary research. So now, let me introduce the first panelist. Professor Gong Peng is an ecologist. He's the director of the Center for Earth System Science at Tsinghua University and a professor at the Department of Environmental Science at UC Berkeley. He will remark on how does computer change all disciplines in science. Let's welcome Professor Gong.
Well, good morning, everyone. It's an honor to be here to comment about interdisciplinary science and collaboration and using computer science. I'd like to start with just a couple introduction remarks about our organization, my research unit. It's a newly founded research unit on the Tsinghua campus, specializing on global change studies, basically, global environmental change. So in order to do that, we house, just like what the earlier presentation are promoting, we house an interdisciplinary group of faculty members in the same center. We have people who work on climate change, who work on Earth observation, who work on economics, who work on geography, global ecology, and computer science. So we do have, in our 27 faculty members, we have 5 faculty members who has PhDs from computer science. And they are recruited, these faculty are all recruited from all over the world. So that's basically how interdisciplinary we are. And I really advocate, in order to promote this, even at Berkeley, we dreamed to be able to, for environmental scientists, to work with computer scientists, for example. It's actually very hard. We are separated from different ends of the campus. And here, we are all on the same floor of the building. This has brought us tremendous advantages for people to exchange ideas and to quickly act on problems that we are facing to solve. So I like to take this basic to expand a little bit about computational thinking to say that under our roof, we talk about spatial and temporal thinking. We're facing with a problem that are so complicated. We are asking questions basically that will help us to map into the future. So mapping has been talked about, and you see maps that are static on the screen. And we are indeed facing with problems, just like Tim has been raising, that people, climate modelers, have produced such a huge amount of data, but how are we going to automatically analyze them, to make efficient use of the data? So we have exactly those kind of problems. But to frame these questions, I think it will be helpful for this audience to think about the kind of big questions we have in our field. So we try to ask questions related to what would the future climate be in the next few weeks, in the next few decades, in the next century. We also want to ask questions which is even bigger, such as, will we sustain on Earth? Do we need to migrate to Mars or other planets? So those are the kind of questions that are related to my colleagues. So in order to do that, the approaches we try to take is obviously simulation. Simulate some of the past and also to be able to predict and project into the future. So simulation, prediction, and projection, none of them can go without the engagement of computer science. So we are all familiar with this kind of general paradigm of from data, we need to observe, collect, to computing, and then to new data or information or knowledge. So this is basically a general three-stage in scientific research. I don't have to exemplify or generalize or give you specific examples. Previous speakers have already made so many examples. So, but to just synthesize in this, you can imagine the kind of data we are going to use in our Earth-related scientific questions are not only natural, physical world data, the climate, the vegetation, the soil, the kind of water we face, but also the population growth, economic development, there are globalization, and human behavior. So all of those data need to be collected and assembled in a certain way and pass that into computing to give us new data, new information, new knowledge, eventually to support us to do decision making. So that's basically, in our field, computer science, computer technology, computational thinking plays a critical role in our research. So in a sense, in today, we are really lucky. We have so many sensors, including our mobile phones. We could collect images. We could get so many data, so much of that for now. But if we go back for 50 years, if we go back to 100 years, if we go back for 1,000 years, or even earlier, we don't have so much data. So we really need to work in a way like what Jeanette has been arguing. Yes, if we have representative data, We have representative polling, we have representative sampling, that's great. If we don't, we have to live with non-representative data, imprecise, uncertain sources of information. So how would we make use? I think this is a challenge for future computational science. How would we make use of those imprecise, uncertain? Basically, you are living in void. You don't have sufficient amount of data and try to come up with the solid science, accurate truth knowledge. So that's one big challenge, I think, for us that requires interdisciplinary efforts to do that. So take climate change as an example in our field. You see some of the curves already by people predicting the trend of a climate, say take temperature as one variable. When you project it into the future, there's a big envelope. That means you don't have certain trend for the future. When you try to recast that from the past, you have a big envelope because you don't have data. So the envelope narrows only when the time is at relatively recent, or up to date. So this is because we don't have data we haven't experienced for the future, we don't have enough data for the past. So how do we shrink the envelope? It's basically the kind of question I'd like to pose to our colleagues today. And the reason for that, why we need interdisciplinary effort is climate change. Right now, the global warming, there are arguments, and there's even people arguing that for the past 15 years that we don't observe a global warming. Actually, we have cooling. For those of you who are not in this field, I have to argue that the general long trend is that we are going to experience a warming. So there are natural rhythms that are slowing down this whole process or making it appears like there's no warming for the past period of time. Maybe that this trend will continue for another 10 to 15 years. But eventually the whole general trend is increasing. Why are we facing with that problem? There are, like what I said, there is a natural rhythm of climate system. So there are natural factors related to the sun, related to the Earth's self-rotation. And there's also another component, which is human. Two big factors that we have. There's a continuous trend of our biofuel use. Not biofuel, I'm sorry. Fossil fuel use. What we call the carbon emission into the atmosphere. There's another factor, which is basically our gigantic change of the Earth's surface. We call land use, the change of land use. Both of them contribute in various ways, very complicated ways, to the climate system. And we need the computer science to help us to better predict the climate system. Use this as one example in the Earth systems, which requires good prediction or projection of the human activities in order to help us to reduce the uncertainty or error envelope in the past and also in the future. So that's basically my point I'd like to make. Thank you.
Okay, thank you, Professor Gong. And our next panelist, Professor David Rosenblum, is a professor of computer science and dean of the School of Computing at the National University of Singapore, where he also directs the felicitous computing institutes. As a computer scientist, He will remark on how is computer science changed by other disciplines. Let's welcome Professor Rosenblum.
Good morning, everyone, and thank you, Tim, for that introduction. I'll try to keep my remarks brief so that we can get to the panel discussion here. And so as Tim mentioned, I was asked to comment on this question, how has computer science changed by other disciplines? Okay, and I guess, to be honest, and it's probably not too much of a surprise as a computer scientist, my first reaction was to say, well, doesn't that influence go the other way around? Isn't it really computer science that's really changing the world? It's almost a cliche now to make that observation and to talk about how much computer science is changing so many other disciplines. And you don't really have to look very far. You can just look at some of the names of some of these areas of specialization that are emerging in other disciplines. We talk about various kinds of computational sub-disciplines, computational finance, computational biology, computational social science, and other things like digital humanities and robotic surgery, business analytics, cybersecurity. So it's certainly the case, and I don't think anybody would argue, that computer science is having this kind of influence on other disciplines, but is that influence also being felt in the other direction? And I would argue that it is, but perhaps the explanation or the effects are a little bit more subtle and indirect. So a lot of things that are happening in computer science are happening because of interesting problems that are arising in other disciplines. And these other problems are giving inspiration to computer scientists and creating opportunities for new lines of research. And these new lines of research probably wouldn't even arise if it hadn't been for these problems in the first place. Now, earlier on, Jeanette had mentioned some of the successes that have been enjoyed with the Z3 SMT solver. And Z3 arguably was developed to solve a purely computer science problem, and now it's enjoying widespread application in many other different disciplines. And that application in these other disciplines, as she mentioned, probably hadn't even been anticipated at the time that Z3 was developed. But I would argue that there are probably other lines of research that we could identify in computer science that arose purely because of problems that came about in some other discipline. And to give just one example, I have an example up here on the slide of an area where I do some of my own research in mobile computing. So if you look at the history of telecommunications, for example, telecommunications certainly predates the era of computer science. It's had a long and honorable, more than a century history of many important advances for human society. And that history evolved to a point where it was possible at some point for people to start walking around with mobile handsets that would allow them to make telephone calls anywhere in the world at any place that they happen to be out and about. And it was just really a matter of time before those mobile telephones evolved to such an extent that it was desirable to have computational capabilities on those devices. And once we started thinking about putting computational capabilities on these devices and turning them into true smartphones, well, this gave rise to new computer science problems that people hadn't really, that I would argue that people hadn't really been thinking about very much before. Gave rise to the development, for example, of power-aware communication protocols, new kinds of algorithms that would function efficiently in the kind of peculiar resource-constrained environments that exist on smartphones, new power performance profiling techniques for software applications that are meant to run on mobile devices, and new architectural approaches to allocating functionality between client devices and powerful servers that might exist in the cloud, leading to mobile services that are deployed in clouds. So I personally believe that the influences do go both ways, and that a lot of these influences kind of parallel many of the influences that may have been observed over the history of mathematics, where new problems arise in other fields. There's a need to provide new and more rigorous ways of explaining phenomena in these other fields, and that leads to the development of new branches of mathematics or new mathematical techniques to deal with these other problems in these other fields. So this direction of influence certainly, I would say, is bidirectional, and irrespective of which way the influence goes, the opportunities for interdisciplinary research, for other disciplines to have impact on computer science and vice versa, these opportunities are increasing by the day. And so for me in particular, as Tim mentioned, I'm the Dean of the School of Computing at National University of Singapore. So for me in particular, an interesting question is to try to identify what the challenges are that hinder some of these opportunities from coming about, and finding ways of addressing these challenges and removing the barriers so that these kinds of fruitful interdisciplinary interactions can take place. And these challenges are, there are many of these kinds of challenges. Many of these challenges are institutional in nature. It was very refreshing to hear President Jiang mentioning a while ago about how there's a very strong institutional mission to promote interdisciplinarity at Yonsei University. That kind of enlightenment is not something that you find at every institution, and the kinds of institutional and cultural barriers that exist that prevent interdisciplinary work are many, and they manifest themselves in a variety of ways. And to give you just one example, suppose a computer science professor is collaborating with somebody in a medical faculty, and they collaborate on a project and they produce a publication that's published in a top-ranked medical journal. Well, is that computer science professor going to be suitably rewarded for that publication, even though it was outside his or her particular area, traditional area of discipline? Or is that publication going to be ignored, or even worse, are they going to be penalized for having, quote, wasted their time publishing that paper outside their area of expertise? Well, in an enlightened institution, that computer scientist would be rewarded for having that kind of interdisciplinary impact. Other kinds of challenges that arise are perhaps a bit more pragmatic in nature. Nowadays, we're seeing increasing numbers of PhD graduates who have very strong interdisciplinary training, not just in computer science, but in some related field where they do their thesis research. And these people are very much a hot commodity. Everybody wants to hire them, so it's very challenging to be able to just build up ranks of faculty with people that are qualified or have the capability or the inclination to do interdisciplinary work. So the final challenge that's mentioned up here is one that you hear computer scientists complain about a lot. This is the worry or the claim that computer science oftentimes just operates as a service discipline for these other more glamorous disciplines, that we're doing the programming for the scientists or the ecologists or the social scientists or whoever it might be. And I think this is personally, I think this is a pretty narrow-minded view. Certainly there are going to be some interdisciplinary collaborations that have that kind of flavor to them, where the computer scientist is just providing the basic capability and the real research breakthroughs are coming in the other discipline. But in my own experience, and certainly an experience that I've observed in a lot of other people that I know, you can always learn something from an interdisciplinary collaboration. You can learn a lot of interesting things about other disciplines, but it can also give you very new and fresh perspectives on the work that you do in your own discipline if you're a computer scientist. And that experience and understanding will change the way and eventually bring fruitful research outcomes, research results, research breakthroughs in computer science. And so I think people that say this kind of thing, that they worry about computer science being a service discipline to other disciplines, are people that probably aren't so inclined to begin with to look for opportunities to do interdisciplinary work, and instead are just trying to find excuses. So nevertheless, there are challenges that have to be addressed in trying to foster any kind of interdisciplinary work. And I've focused here on research primarily, but the challenges arise also in education. So I think at this point I'll stop and say thank you.
Thank you, Professor Rosenblum. And now I want to invite Dr. Wing and President Zhong come back to stage. Okay, in order to leave more time for the professors to ask questions, give comments, and have some interactions with the panelists, I will simply ask a couple of very simple questions, and then we'll open the mic to all the audience. Okay, the first question I'm really curious is that we all agree that interdisciplinarity is very important, okay, at the universities. Okay, but probably it's also difficult. So I can see some, shall I call that a quick fix? That is in some top universities, there are interdisciplinary schools or interdisciplinary programs. For example, like your institute, which is an interdisciplinary institute. But it seems to me that sometimes the school want to have this kind of cross-disciplinary programs or schools to be a seed so that in the future there will be more interdisciplinary collaboration happening to the whole university. But what we observe is that those interdisciplinary schools or institutes becomes itself an isolated institution. That means they are isolated, although we drew professors from different schools and students, but later it becomes an isolated castle again. What do you think? Is this the right approach to form this kind of interdisciplinary programs or schools? Is this the right approach? Anyone want to share?
Can I say something? I think naturally, let me try to generalize over campuses, universities, and colleges, but it's very hard to generalize, but I will try anyway. You're going to have strong disciplines, departments representing each of the disciplines, and it's very natural to create centers and institutes and so on that overlay across the different disciplines. And I think it's natural, and we should embrace it. And then we should just let upper management, figure out how to ensure that a faculty member who's part of a disciplinary faculty and an interdisciplinary institute really does service to both entities. Now, I spoke as if a single faculty member could belong to two different entities. Again, different campuses approach that in different ways. But that would be one model to foster where you do have a faculty member in a particular disciplinary unit participating in an interdisciplinary institute.
Well, Yonsei University has some experience of operating interdisciplinary education. For instance, Graduate School of Information was founded in 2000. And at the grade school, we host business, economics, industrial engineering, computer science too. So to take this initiative, I think the most difficult thing is to find out faculty members who has open mind, who has commitment, who has take a big challenge to overcome all the barriers. I think that is the important thing. And maybe finally leadership of the university also very important. And if I add one more thing, if we have some time, then I'd like to share 5-minute video, how university can provide more interdisciplinary environment to the student, and how computer science or computational thinking you mentioned can change conventional library to the information sharing, to foster all this kind of collaborative research and interdisciplinary education for the student and researchers. Can you prepare about
Maybe we can do that during the lunchtime?
Yeah.
Okay, yeah, certainly.
Later.
All right, thank you very much.
Could I also
Sure.
add to that a little bit? So I agree with the previous two explanations about that. And I think the very critical thing is whether or not you don't take it just like a fashion or trend, to take it real. In order to engage into real interdisciplinary research, sometimes, from top down, sometimes it's easy to get into, oh, there are different people from different disciplines, let's support them. But then they will bring the resources back and do their own stuff in their own unit. So how do you measure success is actually a very, or success-oriented. To the management, I think that's my observation or advice. And then there's also a very important aspect is from bottom up. You know, whether or not we are really, you know, the strongest from different fields, they have the true desire to solve a real problem that requires interdisciplinary skills. That's really where the hope is actually for the future. In general, this is a trend. We can't stop it. We need to recognize it and promote it. We should respect traditional ways of doing scientific or academic research in their own individual specialized field. But we should promote more people that are targeted toward complicated problem solving that requires interdisciplinary collaboration.
Yes, sure.
So when I first heard your question, I immediately thought of one particular unit within NUS that's very strongly promoting interdisciplinarity. And this unit exhibits many of the positive things you mentioned and perhaps a few of the negative things as well. This is the NUS Graduate School for Integrative Sciences and Engineering, and NGS as it's called. And NGS is responsible for, it runs a program, a PhD program, for students who are interested in doing an interdisciplinary PhD program. So from the outset, they express interest in trying to find problems that cross disciplines and work on problems that have some significant interdisciplinary impact. The unit does operate pretty much in isolation from other faculties on campus. It's very successful at producing PhD graduates that have this interdisciplinary character to them. Where it's perhaps less successful is in establishing links between the faculty members that are doing the supervising of the students. And sometimes also it's, for this particular unit, the students that come in may have interdisciplinary intentions, but then they still end up gravitating toward one particular discipline, and it's sometimes difficult to identify interesting problems for the students to work on that really have a strong basis in multiple institutions.
Okay, there's one very quick follow-up question specifically for Jeanette. Is that I know you have a very long academic background, but you are now working in industry, okay? So if there's someone submit their resume to you and you see this person graduate from a cross-disciplinary school and you are working with Microsoft and you look into this resume, would you think that this guy or this lady is not so good in computer science?
No, I wouldn't think that at all. I don't know. First of all, I would like to remind people that this notion of interdisciplinarity is not new. Many fields that we know and think of as disciplines today came out from the very past from different fields. For instance, computer science. So I'm not sure, perhaps we're making more out of this than really necessary. I still remember at Carnegie Mellon when we were trying to start computational biology on campus. And it was a real struggle because you had the biologists here and the computer scientists here, and they all, say they wanted to hire a computational biology faculty member, and they have different cultures and different evaluation criteria. But eventually, it had to happen. And the two sets of faculty had to get together because that's where the science was going. And the science required the two disciplines, the people in the two different disciplines, to start working together and collaborating. So when I will look at a resume, I'm going to look at not what the person majored in. I'm going to look at the qualities of the person. what kinds of problem-solving skills did this person learn? And interdisciplinary could actually be a benefit. So I wouldn't say, oh, this person has a PhD in, say, computational biology, he must not know computer science. I wouldn't say that at all.
Okay, thank you. Now, sure.
Well, I think, of course, job placement is the most important indicator of performance of interdisciplinary education. Already the leading companies begin to recruit the student with interdisciplinary background. For example, Samsung, the leading company, last year hired about 300 student background with liberal art to make programmer, right? Computer programmer. So the new employees do not have any background on computer science. They have only background on liberal art. But university had not followed the trend of this change. So the leading company, at first, they recruit liberal art students and educate, train at company, and they will use the right person. So I think, in any country, university is very traditional. They have tendency not to change at all. Right? So the leading company go first.
Thank you for your sharing. Okay, now we want to shift the gear from the very high to very practical. That is how to teach a course, okay? Jeanette mentioned about computational thinking in all K-12, things like that. In China, it is actually a required course for all the freshman year, which is the computer fundamental. I hope I'm not exaggerating it, but what I heard is it's probably one of the most boring courses to the students. Okay, a part of it is that students feel that computing has nothing to do with them. Okay, they choose, for example, history major. Okay, what is computing to do with them? Okay, what we have been talking about is more like in the research type of universities. Assume that you are in a very ordinary university, and this question specifically for Professor Rosenbluth, I'm challenging you. If you have to teach a history major students in their freshman year, this computer fundamental, okay, and be reminded this students are very diversified in terms of their knowledge about computing. Some of them are computer geeks because of their hobby. Some of them probably know nothing about a computer and not interested at all. If you have to teach a class like that, what would you do?
Well, let's see. So first of all, I would say NUS is no ordinary university.
Yes,
just
exactly.
to clarify,
So this is a
possible
challenge.
misimpression about that. Yes, I mean this is certainly a problem that arises, and actually it's a very germane question for us at NUS right now. At NUS in the School of Computing, we're very interested in developing a cybersecurity minor that potentially students from a very wide variety of other faculties might be interested in signing up for. And these would be students not just from kind of the usual suspects, engineering perhaps, or maybe business, but also potentially law or public policy, students from a wide variety of faculties. And a big challenge for us in thinking about how to achieve this is just in order to get to the point where we can start to educate the students in the interesting aspects of cybersecurity, they still need a lot of computer science background, programming and data structures, algorithms, just to be able to understand some of the basic concepts in cybersecurity. So it's not an easy thing to do. I mean, certainly you can tailor the technical depth of content to orient an introductory computer science course more towards technical majors or non-technical majors. Certainly a lot of people are able to do that successfully, and to make computer science appealing for those people in the less technical subject areas. But in order to have a richer curricular initiative of some kind, like a minor, for example, in cybersecurity, I think the challenges are much greater.
Mm-hmm. Yes, sure.
I have a very specific example to answer Tim's question. Again, at Carnegie Mellon, by the way, it doesn't have to, anyway, we invented a new course that would be for non-majors that would teach computational thinking or fundamental computer science, that's what we call it, right? Fundamentals of computer science. Because before then, the course was programming in Java. And all students at Carnegie Mellon are required to take this course. So you have artists, historians, musicians, electrical engineers, they all have to take this course. The only major that's exempt from this requirement are the drama majors. Okay, so they get an exception. But in any case, every other student has to take this course. And we in computer science were teaching this new course. And we recognized very early on, after the first semester, that we had to do what you just said, Paul. We had to teach a version that was for the very technical people, like the electrical engineers who already knew how, were very advanced in their reasoning skills and their programming skills, and the non-technical, the more the arts majors and so on. And what you do is you make the homework examples, the homework problems and the problem sets and the projects appealing to non-computer scientists. They could be very well, the questions could be posed in these non-computer science terms in a setting that makes sense and is motivating for these non-computer scientists. And I know that, for instance, at Brown University, there's a course called Computational Thinking for Humanities and Social Sciences. And if you look at all the problem sets, the homeworks that are given, it's taught by a computer science professor. They're all about questions that a humanities or a social scientist would be interested in asking and answering. And then they learn along the way the computational techniques to answer the questions.
Okay, thank you. Okay, now one last follow-up question specifically for Professor Gong, and then we'll open the mic for all the professors' questions. That is, I know your school because we have a collaborative project together. I'm really amazed by the capability, computing capability that your institute have. So I know a lot of your students are not computer science major, and probably a lot of them has nothing to do with computing at all. How would you encourage them to know computer science? And especially for yourself, I know you probably do not have computer science official training. How comes you are interested in this and push yourself to learn?
Well, actually, this is very natural. You know, I could comment a little bit about today we are making such a strong evidence and argument that computer science is everywhere. It affects everybody's life. Now that means in academic ecosystem, it's really high up there. So, and also job market, you know, when people with skills, with computer, and then some specialized skills in earth science, it's a bonus to everyone. So it's not really hard for us to persuade our students to learn more about computing in our field. As a matter of fact, actually, in atmospheric science, for example, I'm wearing a tie from Princeton. A professor who visited us from the GFDL, Geophysics Fluid Dynamics Lab. They are among the first, as early as in the 1940s, when the computers are just about to be getting wider and wider recognition for, you know, the high end, not in the general public, that they practiced ocean general circulation modeling in the hope that to study and understand weather. So computer science is deeply rooted in earth science in that way. So we don't have a lot of difficulties in persuading our students to learn computer science.
Thank you. Okay, now, is there any question from the professors? Yes? Is there a microphone there?
I'm a professor from Zhejiang University. I'm lucky to be involved with collaboration with Microsoft for more than 10 years. But I think computing is a very important science, and it will be more important in the future. But the current issues, current problems, is not to have multiple discipline scientists work together to sit there to solve the problem. The university is the most comprehensive university in China. We have different professors work together, but we cannot solve the problem. I think the most challenge for Microsoft, the #1 leading software in the world, we need to work with Microsoft where to develop some new technology, new software, new tools can predict the very complicated situation system of Earth's future, the future of Earth, the complex society of the future, and the complicated human behavior, human disease. Now we are involved with some e-health proposed by Microsoft several years ago, but still now there is no solution. So the problem is the society, the human, is too complicated. It's a very complex system. It's changed variously. So now there is no tool for computation can predict the future in everywhere, no way. So I think Microsoft needs to work with scientists together to provide some software, some subroutines, some power tools to do that. I don't think that education at the elementary school is very important. Sure, computation is important, but it will not solve the challenge in the future.
So I would like to answer that. In fact, Microsoft does have a cloud platform called Azure, and it is a platform that scientists can use to do analysis over large data, to do simulations and so on. So I think the question you're asking is, so Microsoft provides software platforms and so on so that scientists can use these sorts of tools to do their science. The question you're asking, I hope, is not, Microsoft should solve the earth science climate problem. I mean, in fact, there are scientists in Microsoft Research who are environmental and ecological scientists who are amassing massive amounts of data that's public and building models for predictive power and, in fact, serving this on an Azure platform. It's called Fetch Climate. You can actually go to it and you can do some what-if scenarios and you can do some possible predictions. But it's just a step towards the grander scientific challenge in terms of climate change and understanding the environment, let alone bringing in the human aspect. I mean, you're talking about a huge, complex system that you would like to model and then run under different initial conditions, lots of scenarios, what-if scenarios for predictive power. This is not Microsoft's line of business, actually. But Microsoft's line of business is to provide the software platforms and tools that can enable the scientist to do this sort of work.
Could I, since you brought Earth's future, health problems and human behavior are so complicated and hard to predict, I just want to further a little bit of this argument. First of all, I think there's definitely not enough. You are saying that it's not important for less important. You wish a software company or a computer giant will be able to have a one-suite solution for everyone. That's going to be in the long way, maybe in many years to come. I want to emphasize that I actually fully agree with Jeanette on establishing computational thinking as early as possible, because that's the only way we educate more people, we have more thoughts for the whole world to think computationally, and we could advance and make better use of computing for human society. On the other hand, in our field, actually, I see the necessity of having people in different disciplinaries to sit together. I give you one example that are NCAR people stupid? For those of you who don't know NCAR stands for National Center for Atmospheric Research. It's backed by 70 first grade meteorology departments called UCAR, University Center for Atmospheric Research. These supported by human, by soul, to this particular organization, NCAR. NSF, DOE, support by money to put together that make this 1,000 people organization working since the 1960s, trying to solve Earth modeling problems, basically climate system model. So it's only one part of that, climate system model. But by working with our people, one module of that particular program, when we bring the computer science from Tsinghua to work with us to improve, optimize the algorithm, we increased one big component of that by 17 times. So they have several hundred engineers. They have lots of scientists, but they don't have those kind of eye catchers to debug that particular part to make the program more optimal and efficient. So we need more of that kind of successful examples.
Okay, thank you. Are there other questions? Yes, there's one over there. How about we take that on at the back first, and then here. Thank you.
Thank you. First of all, I would like to state my viewpoint. I would think that the interdisciplinary education is very important. But from all of you guys told me multidisciplinarity is not an innovation. It happens a long time before. And Samsung they will hire the other discipline guys naturally. So it seems that everything happened naturally. So why do we want to emphasize now we have to start the interdisciplinary education now? And why now? Does that mean that our computer science hit a dead end, so we need to find a new direction? I don't know. I want somebody to help me to answer my question. Thank you.
Okay, let me comment first. The reason we are talking about this stage in time is, I think, is probably because of the big data. So the big data kind of making this issue more serious, right? So big data makes all the disciplines kind of getting together. So I think that's the reason we have this topic at this moment.
Could I? Well, I see this differently. I think that indeed the availability of data has come to a point that helps to bring us together. But also, it's been a long dream for people to make powerful computing to solve different problems. You need efficiency, you need accuracy, you need precision. All of that in the past actually are not that desirable or possible. So people think about this, maybe they drop the problem because the tools and platforms are not there. So now it is time that there are lots of things that are possible. Data are available there, speed is there, and so people are coming together to re-examine some of the issues that might have been solved many years ago. But I think it's time for us to act.
Thank you. There's a question here. Yes.
So I'm Professor Kwang Bok Lee from Seoul National University. So, it's very good to be here. It's my first time here. But I have some confusion. Actually, I already had this confusion. The meaning of interdisciplinary talents. Does it mean you like to have an expert in many areas? Or would like to have an expert in one area with some understandings? Because it's not easy to be expert in many areas at once. So maybe it's better to teach students be expert in one area with some understanding in other areas. So what do you think about that?
I think for the purposes of this panel, the meaning of interdisciplinary is someone who is an expert in 2 or more areas. That's my assumption here. And there's a bias in this room that one of those areas be computer science, but that need not be. I do want to remind everyone that in terms of research, if you have a problem that naturally needs people from different disciplines, it doesn't mean you need to hire someone who is well-versed in all those disciplines. You get a team of people together, like an institute, and bring in experts from the different disciplines, sit them together, and get them excited about solving that problem that requires the multiple expertise. Over time, of course, the next generation, the graduate students they produce, will be well-versed in 2 or more of those areas.
Well, in terms of education, I think at the undergraduate level, they should be educated in multilateral subject, because science is changing very fast, and the social problems and issues are very multidimensional. If they are educated at only one major, the future society they will face with the very difficult multidimensional problems, so they cannot solve it. So at the undergraduate level, I like to strongly emphasize the education should be multilateral, interdisciplinary, with a strong emphasis on liberal art. And then at the graduate level, maybe we can educate some specialists with a couple of majors or only one sole major. Then they can collaborate with other majors.
Could I add one more dimension to this, is that we hear diversity, the words, a lot this morning. I think we face with a very diverse world. There are specialists who could go deeper and deeper. We love that. Great, they are experts. There are also generalists who could actually shift from one field to the other. We should also advocate. Our society needs those kind of people. So here, educationers or university, the role of universities should be able to empower both.
Okay, may I consider that as the final question? Okay. All right, thank you very much.
Thank you, and I really have a question about the way of performing the interdisciplinary study and the way of fostering collaboratory research. My personal observation is that for whichever studies beginning from computational ecology, computer earth science, or whatever, I see the computer science are very brave, and they are very good learning new things and new concepts and new ideas from atmosphere science, ecological remote sensing. I see the kind of way of collaborating is kind of that domain experts are striving, understanding the principles, while computer science are having their hands dirty and manipulating with the data all the day and all the way. So in terms of education, do you think this way needs to be changed or not? Is it a good way about?
In the early days of a collaboration between a computer scientist and a non-computer scientist, there tends to be this service component, and Paul talked about it before. But the ideal collaboration is when the two, let's just say it's two as abstracting from the many, learn from each other. And this is what Paul's point was. Computer science certainly is influencing other disciplines, but when we collaborate with people in other disciplines, we want to advance computer science as well. So we want to push the state of the art in our field, in computer science as well. But sometimes, like in any collaboration, there's a little give and take. And maybe in the beginning, the computer science gives a little more than takes. But over time, the hope is that it's symmetric.
Okay, due to the time limit, we ended the panel discussion, this morning session here. And in this afternoon, there will be another panel discussion more on interdisciplinary research, and we can continue with that. So thank you very much, and thank you all the panelists.